In this movie, we're going to discuss the factors that determine the conduction velocity of the action potential. And the bottom line is the conduction velocity is determined largely by the axon diameter, where large diameter axons have fast conduction velocities, smaller axons have slower conduction velocities, and the smallest axons have the slowest conduction velocities. Watch. But why does a larger axon generate a faster conduction velocity than a smaller axon? Well, before I can explain that, let's first consider how an action potential propagates down the axon. And the important point here is the spread of current, because the spread of current, positive current, down the axon opens sodium channels and causes the action potential to propagate along the axon. And here you can see an action potential generated on the left side and some of the current spreading down. And what it's going to do is going to open sodium channels and generate another action potential. And that then is going to propagate all the way down as a consequence of the spread of positive charges and the sequential opening of sodium channels along the axon. The degree to which the current spreads down the axon depends on two major features. The first is the internal resistance offered by the axoplasm, which becomes smaller as the axon diameter increases because the axon becomes larger. And two is the membrane resistance, that is the number of open potassium channels, which also becomes smaller as the axon diameter increases because there are more potassium channels in a larger axon. However, the internal resistance and the membrane resistance act against each other. They act in opposition. The internal resistance of small axons is large. It's large because they're small and it's hard for current to flow down, and that retards current flow. But because their membranes are small, they have fewer potassium channels through which current can leak out along the axon. The internal resistance of large axons, on the other hand, is low, which enhances current flow. It's easier for current to flow down large axons. But because they have more membrane, they have more potassium channels through which the current can leak out along the axon. And the question is, which one of these two opposing features dominates as the axon becomes larger? So the answer is the internal resistance, and the internal resistance wins big. And the reasons for that are diagrammed in this figure. On the left, I have a smaller axon, and the smaller axon has 4 purple potassium channels through which current can leak out of the membrane. The larger diameter on the right is twice the diameter of the smaller one and has 8 purple potassium channels on it. So there are more purple potassium channels through which current can leak out. Now, the membrane resistance, that is the number of potassium channels or number of open channels, varies with the circumference of the axon. And that varies by 2 pi r. In other words, there's a linear change in the circumference of the axon as I double the diameter. That's why I have 4 purple potassium channels in the smaller axon and 8 in the bigger axon. However, the internal resistance, which is determined by the area of the axon, varies by pi r squared. So if I increase the diameter by a factor of 2, I don't decrease the internal resistance by a factor of 2, I decrease it by a factor of 4. So the bottom line is that the internal resistance of large diameter axons is small, so that large amounts of current can spread down the axon, even though some of the current is lost by leakage through the purple potassium channels. On the other hand, if I look at the smaller axon on the bottom, the internal resistance of the smaller axon diameters is large, so that only small amounts of current spread down the axon. Most of the current is lost by leakage, since leakage through the channels in the membrane is the path of least resistance. So the reason conduction velocity is determined by axon diameter is because the larger the axon diameter, the easier it is for current to spread farther down the membrane and therefore depolarize larger chunks of membrane farther along the axon and thus increase conduction velocity substantially. General idea is then that the larger the axon, the faster the conduction velocity. And this is beautifully exemplified by the squid giant axon, which has a diameter of 800 micrometers. That's almost a full millimeter in diameter. The reason it's so large is because this axon is used for escape, and to escape predators you need speed. But imagine if we had axons that size in our arms and in our legs. There are thousands of neurons in each nerve bundle. We would have nerve bundles the size of a tree trunk. We couldn't accommodate it. Indeed, our neurons are terribly small. A mammalian axon, for example, is only 2 microns in diameter. Look at the difference in size between the squid and a mammalian axon. So the question then becomes, how do we take these small axons and have a reasonably fast conduction velocity? And the answer is, to increase the speed of action potentials in small axons, vertebrates invented myelination. And here's what myelination is. To illustrate it, I'm going to take an axon here. And there's the membrane. And I'm going to add to that a myelin sheath. This is just the membrane of a glial cell that wraps around the axon and squeezes out its cytoplasm and creates a multi-layered lipid insulation. The whole idea is that current cannot escape from the axon underneath the myelin sheath. Wherever it is present, the myelin electrically insulates the axon. And then we're going to add a whole bunch of these different myelin sheaths. And if you notice, there are spaces between them, spaces where there is no myelin. And we call those nodes of Ranvier. And then the idea is going to be to stick your sodium and potassium channels at the nodes of Ranvier, and that's where we're going to generate our action potentials. So what we do then is generate an action potential, and you can see the current spreading down the axon. And notice there is no leak of current out of the axon under the myelin sheath. So almost all of it spreads down to the next node. And the idea then is going to be is that at the next node, what you're going to do is then generate another action potential. And that's going to be contrasted with an unmyelinated axon, which has no myelin. And what happens there is you get an action potential, which brings in a lot of positive charge, and that positive charge spreads down the axon, but a lot of it is going to be lost. So the only place that's depolarized is regions of the axon very close to where the action potential was indeed generated. So next, let's see how an action potential is propagated down a myelinated axon. First, we generate an action potential at one node. It jumps to the next node. It jumps to the next node. It jumps to the next node, to the next, all the way down the axon. It's sort of like, at least to me, it's sort of like a kangaroo, just hopping from one node to the next, to the next, to the next, to the next, bypassing all of the membrane that contains the myelin sheath. That kind of conduction is called saltatory conduction, from the Latin saltare, to hop or leap. So the propagation of action potentials along myelinated axons from one node of Ranvier to the next node increases the conduction velocity of action potentials without needing to increase the diameter of an axon. Now let's compare the conduction velocity in a myelinated and an unmyelinated axon of roughly the same diameter. Remember, in the unmyelinated, the current does not spread very far, and hence adjacent patches of membrane have to generate action potentials, whereas in the myelinated axon, huge amounts of the membrane are just bypassed. That is, the myelin parts of the myelinated are just bypassed, and it hops like a kangaroo from one node to the next. Watch. Action potential, action potential, action potential, action potential, action potential. And I'm going to freeze it there. That's the difference in the distance which the action potential has traveled on a myelinated axon compared to an unmyelinated axon at the same time. And you can imagine if the axon is long, that distance is going to increase markedly, and hence the myelinated axon is going to be much faster than the unmyelinated axon. Just as it was with unmyelinated axons, larger myelinated axons have faster conduction velocities than smaller myelinated axons. Watch. It's going to be fast because the current spreads down the membrane very quickly, as opposed to the smaller one, which just takes a longer amount of time to depolarize.